For today's lesson, we're going to be talking about what it means to be at equilibrium and how we can adjust equilibrium or shift it from the left or to the right. Normally, we talk about reactions, we think of them as going one direction, from our reactants to our products. However, almost all reactions are reversible depending on how much energy you have to put in to get the reaction to work. So for example, SO2 and oxygen can form sulfur trioxide, but sulfur trioxide can decompose back into these two. And it reaches a point where there's a balance between the forward and the reverse. So reversible reactions are represented with this double arrow. So equilibrium is a state that's reached between the forward and the reverse reaction. So it's a state of rate balance, meaning we were converting the same amount forward as we are backwards. So the rates of the forward and the reverse reactions are the same. So if we think of like escalators going up shoppers going up an escalator, if it was to be at equilibrium, as one person steps off, another person steps on, and that remains, so that the amount of people going up and the amount of people going down remains the same. So the rate is the same. So if two people step up, two people step back on. So there's a balance between the rates, not necessarily the amount of people on the escalators, but the number remains the same. So if there are 10 on the left and 3 on the right, that amount stays the same. So what does it mean to be at equilibrium? And we did that activity last class that described what it means to be at equilibrium. So the concentrations of our reactants, my brackets mean concentration, so the concentration of our reactants and products does not change. So if our reactants have a concentration of 2 molar, they stay at 2 molar. Our products have a concentration of 10 molar, they stay at 10 molar. So the concentration does not change. It appears that the reaction has stopped. So if we were to look at this, the color wouldn't get deeper or darker. It would kind of look like it's staying the same. But it's actually continually moving. So reactants are continuously being converted from our reactants to our products. And our products are doing the opposite, being converted back into reactants. So it's what we call dynamic. So it's always in motion. So there's always being a conversion. Reactants get converted to products, products get converted back into reactants. So it's continuously doing that conversion, but just at the same rate. It also indicates when we're at equilibrium that the ratio of our reactants to products is constant. And we demonstrated this last time in the activity. So here this little simulation is going to show us what it means to be at equilibrium. So here we're starting with all reactants and no products. So we only have a forward rate right now. Now that we have some products, we can have a reverse rate going backwards. Not as big because there's not as many right now, but we still can have a forward and reverse. Over time, we notice now our amounts look the same, but our rates are still not the same, so we're not at equilibrium. But we notice the arrows are getting closer to being the same size. Once they finally reach the forward rate and the reverse rate reach the same length, we now know we're at equilibrium. So they're equal. But what is equal at equilibrium is only the rates. We notice the amounts are not equal. Okay, we have a lot less reactants, we have a lot more products, but the rates are equal. The volumes won't change anymore, so they'll stay constant. Our concentration, amount of reactants and products will remain the same, but they are not the same. So the only thing that's equal is the rate. So what would this look like graphically? So here we notice our concentration versus time. A decreases, but it reaches a level where it plateaus off. B increases, again, reaches a level where it plateaus off. And if we look at the rates of A start really high and then all of a sudden they decrease. B does the same thing. When we know we're at equilibrium, our concentrations no longer change and our rates are the same. So how can we adjust a system when it's at equilibrium? What if we disturb it? How does it get back to equilibrium? So Le Chatelier's principle is going to help us determine what happens when we mess up a system that's at equilibrium. How does it restore itself? And it's always going to restore itself to be different than the original system was. So here's a picture of the French chemist Henri Le Chatelier, and he studied how equilibrium positions shift when we adjust them or we disturb them. So his principle states that if stress is applied to a system, so we're saying stress, we're talking about changing the temperature, changing the pressure, changing the amount of substance in our reaction. So if a stress is applied to that system in equilibrium, the system is going to shift itself so that it relieves that stress. So it's either going to shift more to creating more products, or it's going to shift to create more reactants. So here are some of the stresses that can upset a system at equilibrium. One is changing the concentration. So we add more reactants, we add more products, or we remove some reactants, we remove some products. We can change the temperature, so we can heat up the reaction or we can cool it down. How is that going to affect our system? We can, if we're talking about a gas system, we can change the pressure or the volume of the container the system is in, and that will affect equilibrium. And also adding a catalyst. How does that affect equilibrium? So we're going to talk about these 4 things. So the first, how does changing concentration affect equilibrium? So Le Chatelier stated that when a reactant or product is added or removed, it's going to shift the equilibrium to relieve that stress. So if we add more, so we got to think of our equation kind of like a balance. Okay, so it has to balance itself. Like if you're trying to balance a pencil on your finger. So if we add more carbon or C, substance C to this side, our balance becomes uneven. So this side is too heavy. So in order to relieve that stress, it's going to convert some of our products into our reactants. So it would shift right. And I'm just going to put an R for right. So if we add more of this, let's say we were adding some A instead. So now, or think of it like a teeter-totter. So now we have too much on this side. So in order to relieve that stress, it wants to convert some of A and B back into C. So it would shift to our left. If you add some to the, shift to the, I did that on reverse, I'm sorry. Shift to the left on this one. Shift to this side. My arrow pointed right, but I said the wrong direction. And then this one, we're going to shift to our right, away from the side we added to. So what happens if we remove something? So if we take away C, we remove some of it as it's being made, we remove our product. Now we have a hole on this side. So we have not enough C. So again, it's going to shift to the right if we remove something. Let's say we remove B. If we remove B, again, it's going to convert some of our product back into reactant to make more of it. So it would shift left. So whatever side you add to, it's going to move away from. Whatever side you remove to, it's going to go back and fill in and make more of that. Next, let's discuss how temperature affects our equilibrium. So temperature is going to be dependent on what type of reaction we have, if it's exothermic or endothermic. So remember, a lot of times we tell exo or endothermic by our value of delta H. So if delta H is negative for its value, then we know it's exothermic. If delta H is positive, then we know it's an endothermic reaction. So we have to think of heat as just like being a substance, A or B. So if it's exothermic, heat is leaving. So heat becomes a product. In an endothermic reaction, we need to consume energy. So heat is thought of as a reactant. So just like in our last example where we were moving or adding a substance, heat we can add or remove, and it's going to do the same shift like we shifted in the last one. So Le Chatelier's principle states that changing the temperature will cause the equilibrium to position of a reaction to shift in the direction that relieves that stress. So if we're adding heat to an exothermic reaction, it's going to shift away from it because now we have too much on our product side. So it would shift left. If we add heat to a reactant or to an endothermic reaction, which is a reactant, again, it's going to shift because we have too much on that side now away from it to our product side. So it would shift right if we add heat. Let's say we remove it or cool down our reaction. So if we remove heat in an exothermic reaction, it's going to shift to the right to relieve that, to make more heat. If we remove heat in an endothermic reaction, it's going to shift left to make more heat. So just like in our concentration example. Okay, what about pressure or volume? How do they affect a gaseous reaction? So we have to remember Boyle's law. Remember, Boyle's law was pressure-volume relationship. And it's an inverse relationship, meaning if you increase pressure, you decrease your volume. Or if you increase volume, you decrease your pressure. So Le Chatelier stated, again in this one, that a system will shift in the direction that reduces the pressure if we're changing our volume. So let's look at this example. We have some gaseous substances here. On the left side, we have 2 moles of gas because the coefficients are 1 in front of both of these. On the other side, we have a gas substance as well. It has a coefficient of 3. So we have a 3 to 2, or 2 to 3 ratio, 2 moles of gas things on the left side, 3 moles of gas things on the other side. So let's say we wanted to increase the pressure on this system. So we're increasing the pressure. That means the volume of gas is going to go down. So we're going to be shifting to the side that has the smaller volume of gas. So the side where there's less moles of gas. So in this case, it would shift to the left because there are less gas things. We have to go to a smaller volume, so we need to condense to the side that has the least amount of gas. What if we did the opposite? What if we decrease the pressure? So with our pressure being decreased, we can now go to a larger volume. We can expand more. So we would shift to the side that has more moles of gas. So that would be our right side. Now, what happens if you have a reaction and there are equal moles of gas on both sides? That means changing the pressure or the volume is not going to affect anything. There has to be a different amount of gases for this to affect equilibrium. So if there are equal moles on both sides of our arrow, no change. They have to have a different amount of gas molecules. Sometimes you will have a reaction that only has a gas and a gas, and maybe this one was a solid. So solids aren't affected. Liquids aren't affected. Only gas things, so this would change to 1. Only gaseous things are going to be changed in result of changing pressure or volume. So let's look at this example reaction. So what effect do each of the following changes have on the equilibrium position for this reversible reaction? So let's look at A. So if we add more chlorine, so we're going to add more things to this side. So if we have too much on our right now, so it's going to shift to our left. So we're going to make more reactants. So you can say it shifts left or it shifts towards the reactants. Okay, let's look at B. So B, it says we're going to increase the pressure. So if we remember, if we increase pressure, that means we decrease volume. So we have to go to the side where there's a lower volume of gas. So on our right, we have 2 gas things, so 2 moles. On our left, we only have 1. So if we're increasing the pressure, we got to decrease our volume. So we got to shift to the left again or shift towards our reactants. Okay, for C, we're removing heat. So this one told us it's an endothermic reaction. It told us heat is a reactant. So if we're removing heat, okay, we're going to shift to that side then to fill in that hole that we have or make more heat. So again, we're going to shift left or towards our reactants. And then finally for D, says we're going to remove some of our phosphorus trichloride. So we're removing one of our products. So we're going to shift then to the right or towards our products to make more of that. So when our reaction is at equilibrium, what does this tell us about our amounts of our products and our reactants that we have? How much reactants, how much products do we have? And we really have no idea how much reactant or product we have at equilibrium just by looking at our expression. So how far does a reaction go before it reaches equilibrium? How do we determine that? So we write something called an equilibrium expression, and we find an equilibrium constant, a value. So this is a capital K, and it's just the ratio of our product concentrations over our reactant concentrations, raised to their coefficients. The one thing we have to remember when we're writing these, so our products values, so our products in this case are C and D. Brackets mean concentration, and they're raised to their coefficients. So A and B are our reactants raised to their powers of their coefficients. The only thing we have to be careful with is that solids and liquids are not included. So if any of these were a solid or a liquid, we do not write them in an expression. We kind of ignore them. Solids and liquids don't affect equilibrium. So if we have things that are gases or we have aqueous substances, we include those in our expression. No solids, no liquids. Let's practice writing a couple expressions here for these 2 reactions. So for my first reaction, my equilibrium constant K is my products over my reactants. So my 2 products are on this side. So we have H2 raised to its coefficient. It's just a 1, so I don't need to write a 1, times by the concentration of my other product, so I, which is also a gas, raised to its coefficient, which is 1, divided by my reactant, which is HI, hydroiodic acid, raised to its coefficient. This one has a coefficient, so I'm going to square it. Also a gas. Ignore this as a mistake. So this would be my expression for K, my equilibrium constant. Let's try the second one. So again, I have some aqueous substances, so they're all going to be included. So it's always your products over reactants raised to their coefficient. So I have hydrogen ion, raised to its coefficient squared, times the next product, so SO4, the sulfate ion. And its coefficient is just a 1, so 1 on the outside there. All divided by my reactant, which is sulfuric acid. And its coefficient is 1 again. So that would be my expression for the second reaction. So instead of just writing the expression, let's actually do a little calculation. What is the value of K? So the first step is to always write our expression for K. So in this case, we have 3 gas substances, so all are included. So we have carbon monoxide squared, its coefficient is 2, times the value for oxygen, whose coefficient is just a 1, all divided by our reactant, which is carbon dioxide, and its coefficient is 2. So if we're given some numbers, we can actually plug in and calculate K. So CO, carbon monoxide, is 4. We got to remember to square that. And we're timesing it by oxygen's concentration, which was 1. And we're going to divide that then by carbon dioxide's value, which should have been 4, sorry. And we're going to square that one. And 2 for our carbon monoxide. So we calculate, here's our answer, 0.25 for K. Let's try another one. So we have a colorless gas, dinitrogen tetroxide, and a dark brown gas, nitrogen dioxide. We want to figure out what is our expression for our equilibrium constant, and then we actually want to calculate it. So both are gases, so we want to include both of them in our expression. So we have NO2 as our product, and we're squaring that because its coefficient is 2, dividing it by dinitrogen tetroxide, N2O4. Its coefficient is 1. Now we want to plug in some values. Because this is in a 1 liter solution, our concentration we would have to calculate, which is just going to be the same, 0.0045 moles divided by 1 ends up being the same number. So we'd plug that on the bottom, 0.0045. And our moles, again, we're dividing it just by 1, so to get our molarity, it's the same, 0.03, and we need to square that. We get a value of 0.2 for K. Now let's say instead of a 1 liter solution, this was a 4 liter solution. So you would have to divide by 4 to get your molarity first before you can calculate. So what does this K number tell us? It's a big number, it's a small number sometimes, maybe sometimes it's equal to 1. So if K is if it is equal to 1, if we think about our ratio, because we're calculating a ratio, that means our ratio has to be equal to 1. That means we have the same number of products as we do reactants when we divide the two. So our amount of reactants and products is the same. So our reaction actually lies, we would say, in the middle. If our K is smaller than 1, that would mean, I'm going to write it over here, we have to have a large number on bottom, a large amount of reactants, and a very small amount of product to get a number less than 1. So our reaction would lie to the left, we would say, or towards the reactants. I think in your activity it said it favors the reactants or favors the products. Now, if K is larger than 1, so it's a bigger number, that would be the opposite. So we'd have a very small amount of reactants, but a very large amount of products. So in this case, our reaction would lie to the right, or it would favor the products.